Let's resume with the second talk of the second part, which is given by Michael Zilske from the Technische Universität Berlin, and he will talk about OSM for traffic simulation.
Hi, yeah, thanks for inviting me. Okay, first of all, I'm going to tell you a little bit what traffic simulation is for the kind of project I'm involved in, which is a traffic simulation package, open source, written in Java. And to ease my nervousness, I will just show a little animation. This is the scale of the simulations I'm talking about. So I'm not talking about a driving simulator, nor about a very fine-scaled simulation which contains lane switches and overtaking maneuvers, but about this kind of simulation where people want to do things like being at home, being at leisure activities, being at work. And in order to do these things, they have to move to a city, and everybody else is also doing that. And they share the same traffic system, and we want to know what the outcome of that situation is. And the input to these kinds of simulation is information about who goes from where to where, when, doing what. And the output of this situation, such a simulation, or what the kind of questions we hope to answer with such a simulation is, where are congestions? Who is in that congestion? Where do they live? How much time do they lose by being in congestion? Who's exposed to the external effects of the people using the traffic system, like noise and other emissions? And if you include public transit, how full is which bus? And then we can move on and can try to contribute to questions like what happens if we close a bridge or build a new bridge, introduce a toll. That's a very nice thing to simulate because it can have very unexpected effects which already turn up in simulations. Or make public transit free to use, for example. And then think about how would people react to that. And when people react to that, and we look at the final outcome, who benefits from the final situation in comparison with the previous situation. And when you look at policy measures, ideally, of course, everyone is better off after the policy measure than before, but typically there are always winners and losers. When you introduce a toll, people might drive around that road and go through areas which previously didn't have a lot of traffic, and suddenly people who live there are exposed to more noise, and they would certainly not vote for that measure. And the input to such simulations is twofold. First, we need demand data, and then we need supply data. The demand data is the kind of activity patterns which I was talking about. So you need this kind of information. You need timed activity diaries of people, preferably with the mode of transport they are using, the reason they are traveling, the times at which they are traveling, and where their activities are. You either take these from a survey. Many communities do regular travel surveys, typically about 1% sample size or less maybe. Or you synthesize them, and that works approximately like creating Dungeons and Dragons characters. So you have a set of rules, and you can draw from this set of rules, and what comes out is a person with a realistic activity chain, and the next one, and the next one, and the next one. And you can synthesize cities with realistically looking people doing realistically looking things. And now what is the simulation about? The activity chains and the demographic attributes, as I said, either from survey or synthesized, we typically consider them fixed. And the routes people take, and possibly the mode of transport they are using, we consider flexible and to be outcomes of the simulation rather than inputs. And how does that work? Well, first of all, there's always this economic assumption in there that people use the best option available to them, or known to them. But consider what would happen if you take, for example, OSRM and let the population of a whole city choose the best, let it calculate the best route for the population of a city to choose, and then you simulate the people using these routes. The outcome of that will be that there will be enormous congestion, and people can't possibly use these routes in the way they were planning to. So choices, i.e. which route to take, and the state of the traffic system, which is the outcome of all the people making those choices, need to be consistent. So the travel times our router uses in order to make route suggestions should be the same travel times which then emerge when people follow these suggestions based on these travel times. How do you come to that state? By a little heuristic, we simulate. Then we feed the travel times which come out of the traffic flow simulation, which I'll say a little bit later on, back to the router and repeat and repeat and repeat and repeat. And eventually this procedure converges to something like an equilibrium where people actually experience the travel times with which they were planning. You can program that in Java using, or any other language for that matter, with tools which are partially already available. And the final output of a simulation is then a timeline of all the events on a person level. So you have people ending their activities, departing, entering their car, going through the system on a link-by-link basis, and arriving at their final activity location at their destination. And then you can take that output and make all kinds of analysis on that. You can aggregate that back by where people live, by socio-demographic attributes, by activity types, and so on and so on. Okay, how does OSM help? It helps a bit with the activity generation phase. So when you have these surveys and you ask people, where do you live, where are your activities, you typically get that on the level of some zones, which already exist for some purpose. They may be coarse-grained or fine-grained. But when you want a realistic-looking simulation, you need actual activity locations, as in coordinates. And you can either pick them at random, uniformly. That would look something like this. Or you can use OSM buildings and land use tags and have people only live where people live, according to OpenStreetMap. Or shop where there are shops. And suddenly the picture completely changes if you distribute activity locations in that way. Now this was, alas, not done with OSM data, but this could have been done with OSM data if for this study region it wouldn't have been the case that commercial data still looked a bit more complete. But where OSM helps a lot, actually, and goes practically all the way, is with the supply data, with network data. What kind of attributes do we need for roads? As I said, we simulate the traffic flow. We do this based on only 3 attributes. That is the free speed of a road segment, which, as one speaker already remarked, is not the same as the legal speed limit, but can be sometimes inferred from it. And then we need one other important attribute, and that's the capacity of the road segment in vehicles per time. So how many vehicles can pass this road segment per time unit? And that can, in a similar way, also be mapped to OSM road types pretty usefully. And then there's one final attribute, which is when the link is full, no more vehicles can enter, so we need the length of the link, but that is obvious. And then you get, and when this effect occurs, you get spillback. So, and we get all these from the highway categories. So we have some kind of mapping from highway categories to typical free speeds and typical flow capacities. And the one-way attribute is also pretty much usable. And so we get our road network. What we then typically do is, for example, if we want to consider the city, we take a very much larger area, for example, the entire country, take the main roads from there, and take all the roads from the study area. This is an important step because when you consider through traffic, through your study area, you would like to know where the people are entering and leaving. But now, public transit. And we've been doing the road network part for several years successfully now with only OpenStreetMap data. But public transit is still a bit more tricky. So public transit, at least in our simulations, has the following properties. It goes by a schedule. In our simulation, individual buses are simulated that drive around. They can be full, right? So no more people can enter. They take time to serve passengers, right? So when more passengers want to enter, the bus takes a longer time to have them enter. People can miss buses. And of course, people can have different preferences, for, like different settings for their public transit router, basically. So are you sensitive to line switches? Do you want to have the fastest route at any cost, and so on and so on. And the buses interact with individual traffic. Now, in many cities, this may not be that important because those properties are fixed, right? If you've got a schedule, you expect the buses to be on schedule, and if not, it will be due to a disturbance, but not in a systematic way. But this is not the case everywhere, especially if you want to look at planning situations. So what if we double the rate of buses on a certain road segment? It may very well be that you get interactions with private traffic then, and you will have private cars caught in congestion between buses. And so ideally, we would like bus routes fully linked to our road network and have them go on the real roads, serving real stops, which are at the real sidewalk, at the real link, and not do anything virtual in between. And this already brings me to a bit of software with which we started a bit ago with Nico. Nico is here. We needed visual feedback for that, right? So we figured we would write a JOSM plugin, and the road network part of it is already pretty stable. So you can preview the link attributes, free speed and capacity, of which I was talking. So you can preview the way our data model interprets the OSM attributes, and you can make little changes there and directly save the network and validate it before. And it looks like this. So you can browse your the network you're editing here, and now you also get public transit, and there it gets interesting. Because when you, for example, download the network of Berlin-Brandenburg, a little bit of overpass, you get buses. You look at a single bus route, it looks like this. Of course, every tagged bus route in Berlin is that cleaned up. Public transit version 2. And when you simulate it, it actually seems to work. So we've got a little bus coming there. It's going that way. And there's one in the other direction, and they actually follow their directional route variants. This, of course, only works when the public transit tagging schema is very correctly and thoroughly used, and in Berlin that isn't the case for one single route. So we did this one manually. So there's there are projects like PT Assistant, which was already mentioned here several times, which is great, needed, appreciated, and the step it takes, which is introducing intermediate data model to do validation. What is the stop area? What is a stop post? What is a directional stop, and so on, is really, really important. But then we also need a schedule, right? And Berlin is one of, last time I counted, 2 places in Germany which have public GTFS feeds. So we have the Berlin-Brandenburg area, and we have Ulm, who I think were the first one to publish GTFS, which is nice. And when you now want to match GTFS routes onto OSM routes, you get a whole new set of problems, which is that GTFS and OSM sometimes have different, or not so much the data format itself, but the people who wrote the GTFS feed and the people who tagged the GTFS routes sometimes have different ideas about what a stop is versus what a stop area is, and not even the levels match sometimes. So, and also I only found 2 places in the entire world where any public transit entities in OSM seem to have any kind of information about corresponding GTFS IDs attached to them. I was wondering, what do you think would the prospects be of an effort like, let's finally finish tagging our transitsystem.org for single cities, right? You probably can't do this on a larger scale because you have to consider the intricacies of your particular area. And then try and take this PT Assistant approach and maybe our custom editor approach a step further and make city-specific tools which with a common sort of toolkit which can be adapted to more cities and to finalize OpenStreetMap tagging. Now I realize this is a very specific use case. Maybe not many people are that much interested in buses precisely following the road network, but even if it's only for visualization, it's a very nice thing to have, because when you put people in planning situations and ask them which situation would you prefer, having the bus go this way or that way, it's vitally important to have realistic visual feedback, because if you do tricks there, people will just say, the bus line I used doesn't look like this, and will not become involved. So I think this alone is an argument for trying to finish this. And yeah, our simulation, which does public transit and individual vehicle traffic, is free and open source, focus on GitHub, but you need some kind of input data. You need these activity chains. You can guess them. You can use coarse-grained data like workplaces and homes and just link them and create home trips, and then you already got something to start with. It's not a GUI-based tool. It requires scripting to create your use case. But you can do interesting experiments with it. Like if people are this or that price sensitive and you expose them to this or that evening toll, what will they do? Yeah, it's heavily XML based. That's why we did this graphical editor experiment, which turned out good. And yeah, that's it. Thanks.
Thank you for the talk. Are there any questions?
Great talk, by the way. I only have 35 questions, but I'll be quick. How many agents can you simulate, and how large of a network can you actually deal in your simulation? And do you have any parallelization, some way of making the agents talk to each other and so on?
Yeah. I can easily simulate on my laptop the typical sample sizes from travel surveys. I can, on a largish desktop machine, simulate an inflated population of perhaps a 10% sample. And with much care and very big machines, we can simulate 100% of cities, not of countries. That's approximately the scale. The parallelization, yeah, since this is iterative, replan, simulate, replan, simulate, replan, simulate. The planning steps of the agents you can trivially parallelize. They plan independently in every iteration, so that's easy. The flow simulation is very hard to parallelize. We don't get much better than 1.8 times the sequential version in our experiments, so it's really bad.
You mentioned loading XML data for population. How much are you able to estimate where people live strictly based on OSM data? Like, are you able to simulate the whole thing strictly from where OSM shows people living and shops and offices?
We typically start with some kind of survey population from a formal survey. The problem with these is that they have very low sample sizes. So we want to fuse them with other data. And from the outcome of this data fusion is then an inflated sample. And for this semi-synthetic population, we need activity locations, because I can't have the 10 clones of my survey person all have them live in the same house, because that doesn't work. So we have to redistribute them, and that's what happened in the step which my slide was about. So this is always a bit. It depends on the exact input data which you have, and then you have to ask some statisticians and ask them if this is more or less sound what you're doing, and so this process is always individualized. But OSM helps with not having people live in the middle of a lake or in an industrial area, which already is a long way.
I wanted to ask, what is the model of the simulation? Like, is a Markov chain, a Markov model in a way of, like you were saying that when the road will be like 6 persons, 6 cars, no more cars will come, or how is the logic behind it?
The cars which travel on the network, they are direct results of simulated people doing things. So everybody has their daily plans in beforehand. So there's no, after the plans are fixed, there's no random process anymore. People plan, and then the synthetic reality tells the people how long they are in congestion on which link. And then they experience that, and in the next iteration, they do it differently.
Thanks, great talk. So you currently have like this way of deriving speeds from the road class.
Yes.
Did you experiment with better speed values from real vendors? And okay, no. That was a no, or?
I personally didn't, and my office neighbors, I think, also didn't.
Okay, but what I would be interested in, the traffic simulation, does it simulate things like rush hour then? Or would you be able to, basically having a set of speeds, derive other information for areas where there's no coverage for speeds?
Yeah, well, the rush hour phenomenon is what we hope is endogenous to our simulation. So we want the rush hour to actually happen in this situation. We don't want to need input data for that, in addition to the travel plans of the people. So we are not so much interested in, only for validation purposes maybe, or calibration purposes in dynamic travel times. For us, these two attributes, free speed and capacity, are enough, and they should be static. And the dynamic aspect should be endogenous to the simulation, ideally.
Hi, yeah, thanks. What is your model for mode choice? Obviously, there's vendor lock-in, or so what you said is the best choice. How do you determine what is the best? Once I have a tool, then probably I'm going to use that tool, as opposed to every morning deciding on my trip.
Yeah, depends on the scenario, of course. Sometimes we just leave it fixed. We say people only change their routes, and for the kind of trips we're modeling, and for the kind of time frame we're modeling, they'll basically not change that habit, depending on the question we answer. When we open mode choice as an endogenous choice, we need some estimate for people's utility function. We think that everybody has a utility function which is some combination of the disutility of owning a car, the disutility of spending money on public transit, the disutility of spending time in different modes of transport, and the disutility of being late to an activity. And these are all parameters which need to be estimated from surveys, basically, or tweaked until it looks realistic what comes out of it. But technically, this is what's happening. So our agents calculate their utility based on parameters which you can set, and they optimize for that.
Last question over there.
Did you ever run into instances of the brass paradoxon?
Yes. One colleague of mine is trying to. I hope I summarized this correctly. I think I won't even try. She's trying to find real world instances of the brass paradox in data we have. Yeah.